Hello everyone, this is Tech Talk Universe. Through the Hubble Space Telescope, humans have observed billions of galaxies. Is it possible that there are antimatter galaxies among these galaxies? Scientists believe it is unlikely because Hubble has captured many galaxy collisions. If there were collisions between matter and antimatter galaxies, the resulting energy would be astronomical, even lighting up the entire universe. However, just because we have not found any evidence does not necessarily mean they do not exist. Antimatter has existed for 13.8 billion years, but humans have only discovered it in less than 100 years. Recently, scientists have proposed the hypothesis that the key to studying antimatter lies in whether it is affected by gravity. If antimatter is anti-gravitational, it would completely change our understanding of the universe. To understand antimatter history, we need to start from the beginning. First, let me introduce an experiment, an ion trap. Scientists use this trap to capture many particles, and it looks like there are many small green sticks in a glass tube. Those are not sticks, but particles moving up and down within a certain range at high speed. This looks like a stick due to its velocity. Scientists can also fix the particles in a small range and adjust the number of particles trapped. They can even excite a large ion cloud by adjusting the magnetic field. However, what we see now is not a real ion trap. What we see are pollen particles that are super large compared to quantum particles and easy to observe. We use this pollen trap to demonstrate how an ion trap works. In simple terms, an ion trap is a device that uses a magnetic field to trap charged particles within a certain range. This is a crucial device for studying antimatter. Antimatter is a difficult concept to understand, like a world in a mirror that looks the same as our world. But antiparticles have opposite electrical charges and parity transformations. When matter and antimatter meet, they explode, releasing energy and light. Antimatter cannot be seen or touched, and it was impossible to observe it 100 years ago, so how was antimatter discovered? Antimatter first appeared in a prophecy book called Mathematics. The year was 1928, and British physicist Paul Dirac attempted to unify relativity and quantum mechanics. He formulated the Dirac equation, which is often hailed as one of the most aesthetically pleasing equations in human history. It is comparable to Einstein's EOC2 and Euler's identity. Yang Jianing, a famous physicist, once said that the Dirac equation is so beautiful that it brings tears to the eyes of those who understand it. This equation reaches into the depths of the soul and unlocks the mysteries of the universe. In this equation, Dirac discovered that alpha, and beta, do not have real or imaginary solutions. But by using a 4x4 matrix, the problem can be solved perfectly. Matrices describe the state of an object when it rotates. They show that electrons have two spin directions and carry both positive and negative energies. However, Dirac faced a dilemma. What is negative energy? Does it represent an electron carrying a positive charge? But where is the positron? If there is a position in this world, why has it never been observed? Nevertheless, Dirac had confidence in his equation. After careful consideration, he predicted that there must be positrons in the universe, which are anti-electrons. This was the beginning of antimatter discovery by humans, not through experimental observation, but through mathematical prediction. 4 years later, in August 1932, young physicist Carl Anderson announced a significant discovery to the world. Using the most advanced photography technology at the time, Anderson photographed a cloud chamber in an electromagnetic field. Anderson was surprised to find that an electron had taken the wrong path and was moving in the opposite direction. This article had the same mass as an electron, but its charge was opposite, indicating it was a positron. This is the photo of the position taken by Anderson in 1932. The photograph shows the positron's path through the cloud chamber. Anderson's discovery of a previously unknown particle was significant. He thought of Dirac's prediction that positrons existed in the universe, which meant antimatter. This discovery made the world more complicated than we previously thought. Anderson was awarded the Nobel Prize in Physics in 1936 for his discovery of the positron. Let's briefly introduce what an antiparticle is. There are two main differences between an electron and its antiparticle, the positron. First, their charges are opposite. Electrons carry a negative charge, and positrons carry a positive charge. Scientists call this a charge conjugation, represented by the letter C. Scientists often use a Taiji diagram to explain this concept. The left side of the first picture shows a white fish with a black eye. In contrast, the left side of the second picture shows a black fish with a white eye. Second, the directions are different. In the three-dimensional coordinate system of particles, every direction has an opposite direction. Matter and antimatter must be reversed. This is called parity transformation, represented by the letter P. We can use another Taiji diagram to explain this concept. Not only do the left and right of the black and white fish need to be reversed, but also the top and bottom need to be inverted. Only when both conditions are met can they truly belong to matter and antimatter. Physicists call this CP symmetry. In 1955, scientists at Lawrence Berkeley National Laboratory discovered antiprotons. In 1957, another pair of scientists at the same laboratory discovered antineutrons. 30 years after Dirac predicted antiparticles, all the basic components of the antimatter world appeared. These components were positrons, antiprotons, and antineutrons. This indicates that the laws of the universe allow the existence of antimatter atoms, which are the basic building blocks of the material world. This also means that there may be an antimatter world in the universe. Is it possible that the Hubble telescope captures antimatter stars or even antimatter galaxies in deep space? Scientists want scientific experiments to verify this hypothesis. In astronomy, there is a major field of study called astrophysical spectroscopy. By measuring visible light and radiation using spectroscopic techniques, many properties of stars and galaxies can be calculated. For example, our Sun is mainly composed of hydrogen and helium, with hydrogen accounting for nearly 3/4 of the solar mass. How do we know this? It was calculated using the Sun's spectrum. Here comes the most crucial point. If the spectrum of antihydrogen atoms is different from that of hydrogen atoms, we can use the spectrum of antihydrogen atoms to find the antimatter Sun. This is indeed an excellent idea, but how can we measure the spectrum of antihydrogen atoms? Scientists have spent more than 20 years researching this experiment. Now let's return to the ion trap mentioned at the beginning of the program. The year is 2016, and we are at the Alpha Laboratory at the European Organization for Nuclear Research, CERN, which is currently the world's top antimatter research institution. Their chief scientist is a Danish man named Jeffrey Hangst. As early as 2010, Hangst's team successfully captured antihydrogen atoms, but unfortunately the duration was very short. They spent 6 years improving the ion trap and achieved a significant breakthrough in 2016. Their ion trap can now trap antihydrogen atoms for more than 1,000 seconds or nearly 17 minutes. This is a significant improvement over the previous record of only a fraction of a second. This 17-minute window is significant because it allows scientists to measure the antihydrogen atom spectrum using spectroscopy techniques. In early 2017, Hans Georg finally obtained the antihydrogen atom spectrum. They found that antihydrogen's spectrum was identical to that of hydrogen, meaning that we cannot distinguish between antimatter and normal matter by different spectra. Although this was a disappointment, it also confirmed that CP symmetry laws are strictly followed by matter and antimatter. However, this led to an additional problem. If there is no difference in the spectra between matter and antimatter, who can guarantee that the light coming from distant galaxies is emitted by normal matter? Maybe there are antimatter events, but we just can't distinguish them. This increases the possibility of the existence of antimatter galaxies. According to current mainstream theories, matter and antimatter were generated equally during the Big Bang 13.8 billion years ago, and they constantly annihilated each other. However, due to a currently unexplained reason, matter and antimatter decay processes differ. Approximately every 10 billion matter-antimatter annihilation processes, one normal matter particle is left behind. This was deduced from the law of parity non-conservation by physicists Li Tsung Dao and Yang Chen Ning. The energy produced by annihilation becomes the microwave background radiation that pervades the universe, which we can detect at any time. The remaining normal matter eventually formed matter in the universe. According to this theory, there is very little antimatter in the universe, and it cannot form antimatter planets, let alone antimatter stars or antimatter galaxies. This is currently the most consistent theory based on scientific observations. However, scientists are still searching for other possibilities to explain antimatter's existence in the universe. Gravity is another important puzzle to solve. Newton told us more than 400 years ago that matter falls under gravity. Since matter and antimatter have strict symmetry, antimatter should fall towards anti-Earth, which means that under Earth's gravity, antimatter should rise and escape from the Earth, not fall. This is a very imaginative observational experiment. However, at present, only ion traps can be used to capture antimatter, which is under electromagnetic control. No one and no institution can complete this experiment. Even after more than 90 years since the discovery of the positron, humans still don't know whether antimatter would rise or fall under the influence of gravity. This remains a mystery. If antimatter is anti-gravity, what will happen? At the beginning of the Big Bang, matter and antimatter were constantly annihilated. As time passed, the universe expanded, and the temperature dropped, and the speed of fermionic particles decreased. Under the anti-gravity force, the gathered matter and antimatter began to move away from each other, forming two regions of matter and antimatter in the universe. Our region belongs to the normal matter universe, and the antimatter universe is at another end. As the speed of expansion of space exceeds the speed of light, we can no longer see the antimatter universe. The information you send to us will be lost forever. Assuming there is an antimatter universe, what will exist between normal matter and antimatter universes? Perhaps the matter and antimatter universes are constantly undergoing matter-antimatter annihilation, which will produce an infinite and huge light curtain, cutting the universe in half. That's all for today's program. This is Tech Talk Universe. See you next time.